Okay. Everyone hear me okay? If I can hear myself as well. Everyone learning lots? I think the first thing I learned yesterday was from Duke's presentation that the perfect presentation is 18 minutes long, which means that mine's 38.888% recurring too long. So it's too late to do anything about it now, but without further ado, I'll get stuck in. So I'm going to talk today about our use of Gurobi optimization within genetic algorithms to improve logistics operations or help the design of logistics operations. I'll do a little bit about BearingPoint to start off with. I'll start talking, then move into the challenge that our client asked us to look at for them. I'll look at the various options that we explored before we went with our solution. I'll talk about the way in which we went about crafting that solution, and then a few lessons learned. Some of these will be old and familiar lessons, but it doesn't help to remind ourselves from time to time. So a very quick introduction to BearingPoint, for those of you who don't know us, we are a management and technology consultancy. We're split into 3 divisions. The first of which is our products division, where we develop our own products and implement them with clients. These are a whole range of products that help organizations, businesses to deliver a whole host of benefits. Within that division, we also implement things like SAP, Salesforce, some of the big enterprise platforms. We have a capitals team, which advise on mergers and acquisitions also from a technical perspective as well. We have a consulting division, which is the part of the business that I work in. That consulting division has a whole number of service lines, one of which is the operations service line, which looks at supply chain operations across all different industries, be it retail, manufacturing, utilities, service industries as well. And then lastly, by no means least, we have a joint venture called ArcWide with a company called IFS, where we collaborate to implement IFS enterprise management solutions. Last one on BearingPoint. We are a global consultancy. We're just shy of 6,000 people now, and our revenue's towards the 900 million euro mark. That is it for BearingPoint. If you'd like to know more, then by all means, catch me later. Okay, the challenge. We've got a Rubik's Cube here, which I think has 42 quintillion combinations. I'm not quite sure we were at that level, but at times it did feel quite complex, as I know often some of these optimization challenges often are. So, without further ado, our client is a major grocery and general merchandise retailer, so homewares as well as all of the grocery things you can imagine. They've had quite a significant period of growth, and that is projected by them to continue up for the foreseeable future. They have multiple product types, as you might imagine, and by product types, I mean it could be a frozen product, it could be a chilled product, it could be an ambient product, it could be a product that's none of those but has to be handled at a specific temperature. That's all the way through the chain. And they have some products, again, within the homewares, as you can imagine, that are small, some are big, and some are what you might call ugly in terms of handling characteristics. And they wanted us to help design a new automated distribution center and help them just test that obviously the capacities that we'd spec were correct, and I tease out any bottlenecks and a lot more beyond that I'll come on to see. And this is a distribution center that will be serving many hundreds of stores, as well as elements of hub distribution as well. So the challenge, I've already covered some of this. The challenge that they wanted us to address was to help them define a schedule that meets the store service requirements. So make sure the vehicles are getting to the stores at the right time, that the fresh product isn't turning up at 7 p.m. at night, it's turning up in the morning, and all the other products are getting to store on time. But do that so that you optimize the fleet, and also make sure that we optimize the use of the automation, because one of the things you don't want to do is invest many millions of pounds in the automation, but still then have to have lots of labor at the same time. So it's a balance of these things and more beyond that. So within the operation, there were 6 elements that we looked at. We could have gone into more detail, but as you can imagine, we're already at quite a lot already. So if we think about it with those 6 blocks that you can see on the slide there, so the inbound to the distribution centre, and then we did do a bit of storage, but if we skip that for the time being, there was the picking. So this is picking the products, be it automated, be it manually. Once those products are picked, they can go back into storage until the time is right to put them onto the vehicle. So that's the re-extraction. So we can pick them for the store, put them into storage, and then pull them out a few hours later. That's the extraction. And then there's the loading. So when do I actually start putting them onto the vehicles? Then there's the dispatch of the vehicle, and then there's the final leg to the store delivery. 6 blocks. Again, those of you familiar with logistics operations, warehouse operations, know we could go into a lot more detail on those. But again, we had enough to deal with. So we went with those 6 blocks, having discussed it with the client. In terms of some of the things we had to consider when we're generating an optimum schedule, you can see them there in the grey. So things like, well, when do we get the order release from the stores? So that we can actually start planning these. What are the store delivery windows, and what are the volumes? Have we got sufficient space on the site to park the trailers? Have we got enough electric hookups as well? So if we want to preload a vehicle before it goes to store, can we have the refrigeration unit on in the vehicle before it leaves for store? There's the fleet size. Well, what is the right fleet size? And what's the right mix? Because there might be some stores that can't take an articulated vehicle. Some might have to have a rigid vehicle. Do I do double deck, single deck, all those kinds of things? There's the storage capacities. There's the automation capacities. There's the drive times to the stores, shift labour, and the vehicle costs and the labour costs that you might put in any fairly standard optimization. So the fact that this was automated made it more like a manufacturing operation, rather than just a traditional logistics, a traditional warehouse operation. Covered some of this already, but as you can see, there's we start on the right hand or the left hand side there, where we have the store arrival schedule. We can, if we want to, just follow a fairly standard, backward schedule. We did do elements of this, but as you can see, that what might be optimum for one place here might not be optimum for over here. So there is a little bit of to and fro and linkage required between the two, or between all of these blocks. As I said earlier, that we were looking at serving hundreds of stores and still looking at serving hundreds of stores, multiple delivery slots across the day for those stores, 8 product types. There's the different fleet size and mix, about four or so different types of vehicles. There's the site constraints, not just at the stores in terms of what vehicle they can take, but also the site constraints. So how many doors should the distribution centre have? How many parking bays? How many should have electric hookup? And then there's the time granularity at which we want to model this. And anyone who's obviously done any optimization will know that time granularity can be a major driver of complexity. We started off with 15 minutes, and I think we ended up at 6 minutes in the end. And then the final bit that's not on here is actually we were not just looking at this at an aggregate volume level. We were looking at this from a pallet volume level or a store handling medium level. So that could be an individual roll cage, or it could be an individual pallet. That's the level at which we were optimizing this operation. So there could be 10 million variables involved with this. There actually were a lot more when we did the maths. So again, I don't know if it's 42 quintillion, but it was a big, big problem. So having established that this was a big problem, but something that obviously we wanted to get our teeth into, we started exploring our options, which in traditional British style started with a cup of tea or several. And then we started really getting to grips with it with the data science team and saying, well, what are the options available? First one was, why don't we just stick it all in a single MIP, which would have been ideal, which is what we would traditionally do, having done this with previous clients. That would again keep it quite simple. The less good is we were pretty confident that it would take a long time to solve, having built more simple versions of this. historically. We then said, well, why don't we maybe not put it in a MIP or an optimization? Why don't we do write a heuristic algorithm to do it? But then again, with that, we're still left with, we're going to have to simplify the problem. We're going to be left with some really, really complicated rules. And where do you actually start the heuristic to do this? So then we started thinking about, why don't we create some kind of harness and then have multiple MIPs running? That would allow us to do, elements of parallelization if we had multiple MIPs. Bad side of that is, well, which type of harness? Do we use a reinforcement harness, a reinforcement learning harness? Do we use a genetic algorithm? All those kinds of things as well. So there was still quite a bit left for us to think about. In the end, we settled on having a genetic algorithm harness, and I'll go through that in a little bit more detail. Still does enable us to do parallel runs of multiple MIPs and fire off multiple different permutations of schedules. The only challenge with that is, well, how long is it going to take to converge as well? So in the end, we settled on the genetic algorithm approach, and we started some really, really simple iterations with that, as I think many of us do when we start building these optimization algorithms or optimizations. We start simply, test the constraints, add a few more, and see where we go. So how do we actually then start thinking about representing schedules in a genetic algorithm? So we're going to go back to, I don't know if it's high school genetics. I was reminded of this by our data science team of how genetics work and chromosomes and things like that. So in this case, we started, if you imagine what's behind me as the representation of a schedule, of a delivery schedule, and each one or zero is a binary representation of a store either having or not having a delivery in a given time slot by a given vehicle type. And that's all the ones and zeros represent here. The red line just denotes one store from another store. So our chromosomes were so this is a chromosome effectively. Ours were a lot longer than this. I think our longest ones were 64,000, but that's what we start off with. And that's just a binary representation of those three elements that you see at the bottom of the slide. So how does this actually work? So we start off with, this is a fairly generic introduction to it, but we start off by generating some random schedules with many, many chromosomes. We've only got 2 or 3 there, but many, many, many different versions of those. For the first time round, we actually go straight into the MIP to say, based on these store delivery schedules, give us the optimum DC schedules, the optimum dispatch schedules, all that kind of thing. And then we go straight into the fitness test. That's for the first time round. And then say, well, okay, based on that, give us the best set of store delivery schedules that you can find, or the best chromosomes that have yielded the best DC activity schedules. Obviously, the first time around, we can't see any, it's not starting to converge. So then what we do is we go into the selection state, which says, give us the it's more than 2, give us the best parents from those first set of chromosomes. What we then do is move into an element of exploitation and exploration, where we take the best parents and we cross them over and say, if these are the best parents here, take the first half of one parent and merge it with the second half of another parent, and vice versa as well, to create that to create a new chromosome. We then move into the mutation, which is the exploration side of things. That avoids us getting local optimums as well, and it means that obviously the children aren't too similar to the parents as well. So it just enables us to bring a little bit of variation in. We then come back around and run through the optimizations again, and then that feeds into the fitness test, and we do the whole cycle again to say, were those stored delivery schedules, so those chromosomes, were we able to yield any better DC activity schedules based on those chromosomes? And we go around again, we pick the best solutions, the best stored delivery schedules again, and we go through the MIPs again, doing the exploration and exploitation before that. So that's effectively the harness, and that's a fairly standard approach to genetic algorithms. Maybe don't necessarily do the MIP optimizations there, but that's where we put the MIP optimizations. So how did we actually craft that solution? Similar slide here. So what we did is we said, we have the store delivery schedules there, which represent a store having a delivery in a given time slot with a given vehicle type. We then do a really simple backward schedule, which is something that we would like to have done all the way through this, but we do a backward schedule to work out when the trucks need to leave for the stores, if that's the time at which the stores want the deliveries. We then move into the actual MIPs, where we have a MIP for the loading schedule at the distribution center, and then we have MIPs for the picking of the products, or assembling them onto store cages or pallets for stores. Behind those two boxes, there's actually 6 or 7 MIPs, one for each of the temperature regimes and one for each of the ones that require specific handling characteristics. So we have one for chill, one for ambient, one for frozen, one for the big and ugly stuff, one for the specific temperature regimes, and a couple of others as well. Some of you may look at that and say, well, that's just still a fairly backward schedule. There is an element of linkage between the loading schedules and the other MIPs, where we passed information between the two and actually re-optimize them. So that top arrow there should probably go both ways. I don't want to go into that too much today, but that's effectively what we went through. All of those MIPs then go into the fitness test to say, based on those chromosomes, this is the best schedule I can give you for the DC activities. We then do the crossover, we then do the fitness test, and then say, okay, well, pick the best parents again, and we start that cycle again. We run through the 6 or 7 MIPs again to optimize that. How did we actually go about doing this? Well, we used a fair few different pieces of technology. The first of which was a laptop, where we did some really basic testing, and we did use some, close your ears, Jan, we did use some open source optimizers here, knowing full well we'd come back to yourselves at Gurobi. So we started with Azure. So we went to Azure in the end because that gave us the horsepower for the engine, because what we wanted to do was run a lot of these in parallel. So not just run 2 chromosomes through and see what happened, or 3 or 4. We were throwing hundreds and hundreds at this and running multiple iterations of this in one go. So multiple MIPs at one go. And the guys at Gurobi were great to helping us actually get the parallelization of these MIPs working. In terms of coding, the harness was written in Python. So Azure and the Python to do the harness and to obviously do the fitness tests, all that kind of stuff. And then we use Pyomo. I think I've seen quite a few presentations over the last day or so where people have used Pyomo to feed into Gurobi. We said we generated an LP file here. The reality is we went straight into the Gurobi API. So we tried it with an open source solver, and very quickly we found that it started slowing down, or we just weren't getting the answers, and we came back to Gurobi. We did put quite a bit of horsepower into Azure, and I think probably quite a bit more into the Gurobi. I think Emil, my boss, was looking at it saying, well, how much power from Gurobi you thrown at it, because I can see the bill going up. Well, I don't think we're quite at the highest level of horsepower yet, but it's done the job for us, and it's given us the results that we want. Finally, we then did some visualizations in Power BI to actually figure out what was going on with this, because obviously once we've optimized it, as everyone is when they first do the optimization, you're always keen to see what's happened and to explore the results as well, and get away from trying to hopefully not build a model to explain our model, but we use Power BI for doing the digging there. Just a few basic stats here. So in terms of the chromosome length, as I said earlier, we evolved a series of iterations of the algorithm and of the MIPs themselves. So the chromosome started around about 16,000 long with all of the store combinations, and then as we started changing things like the the time period duration, we actually ended up with about 64,000, and we were throwing around about 96 chromosomes in one go through the harness. What we noticed is that things started to converge after 20 generations. So actually, I think overall the runtime for this was a few hours, but it started to converge after around about 20 generations. We could let it run on forever and ever, I guess, or just to see. But we got to a solutions where each iteration yielded little difference after 20 so generations. In terms of the variables, if we'd put it in one MIP, the number of variables would have been vast. In the individual MIPs, I think the most we've got in one of them is around about 800,000 variables and around about 30,000 constraints. In terms of how many MIPs, the speed, it's our new measure that we talk about now, how many MIPs per hour or how many MIPs per minute we're running. It was around about 33 MIPs per minute with 16 chromosomes in parallel as well. That's after we'd probably up the horsepower a little bit on our original Gurobi subscription. And then MIPs per chromosome, again, it varied between 5 and 14. So as we, again, evolved the solution, we started off with 5 MIPs. And then we went to about 14 again as we started saying, well, these products need to be handled slightly differently. So actually, you're going to have a MIP for that. So it has evolved, and that's through discussion with the client as well. But again, we started doing some fairly straightforward iterations. Some output from some of the scenarios that we've run. So we've run scenarios for this that look at average day, peak day, average day next year, 5 years time, 10 years time. So again, one of the great things about doing optimizations and having this in a harness or in a format that you can run, you can actually test lots of different scenarios for the client, with the client. So what you see there at the top left is one of the outputs from the MIPs and the genetic algorithms. The dark blue line going through the middle there is the automation capacity. The light blue line is actually showing how much manual labor you will need. So this is at peak. So when you design, this is peak day in many years' time. So when you're planning for peak, you don't necessarily design your automation for peak, because if you design it for peak, it's going to be sat idle for a lot. You're going to have a lot of surplus capacity for most of the year. So we expected it to need manual labor in addition to the automated labor at peak day. So what you can see there on that top slide is, on the left is the night shift. The night shift is more expensive, so it's using the minimum labor there. As soon as it kicks into the day shift, it starts throwing more manual labor at it as well. Next to that, you can see that this isn't quite optimized yet, so there's a few dips in there, but again, you can see this is on the ambient side of things. Again, it's tried to minimize the expensive night shift where you have to pay a premium salary or premium wage for night shift. And then you can see that there's still bits where it has to smooth it out and do some further optimization there. At the bottom chart here, you can see this is the vehicles. So split between single deck and double deck vehicles. And you can start to see that when we dug into this a bit further, we were looking at this and trying to understand why it had done certain things. And what we noticed is that actually the earlier it can use the vehicles, the more it can get dual or triple runs out of those vehicles as well. So it's trying to pull as many of those vehicles as early as it possibly can, but taking into account things like, well, what's the picking capacity? How does that balance with the labor I need? All those kinds of things. And then lastly, it's just the delivery schedule as well. Obviously, you can't just have a delivery schedule that works for the DC. It has to align with what the store wants in terms of products being on shelves or products being in store, so that the staff can put those on the shelves in time for the customers to come. We've got some key outputs there. I think we're still sharing some of these outputs, and we've had this running for a considerable amount of time. We're still working with the client to go through, explore some further scenarios as well, validate some of the design. It has identified some of the areas that we knew might be tight during peak, so we can start to work with the client to address those areas as well. And it has provided insight as optimizations do for the various bits, various parts of the supply chain, because again, it's that that conversation on, well, we can optimize this bit, but actually the implication here is this. But actually, by trying to cover as much of the supply chain as we have done, we can really explain that, yes, this might not look optimum here, but overall, it is a better solution. So again, we're exploring those, continue to explore those with the clients, and it's been a really interesting piece of work that we continue to work on with them. Key takeaways. Optimizing the end-to-end operation in small time periods is complex. I think I learned that quite a few years ago, but it doesn't do any help to be reminded of it. Genetic algorithms are a really good way of parallelizing optimizations. And you can trade a single MIP for multiple MIPs if you have a method of doing it like we've done here. And iterative building and testing. So again, as I think in one of the first presentations that was made yesterday, that actually let's start simple, because if we'd gone to the level of complexity that we had now, we'd probably have never understood what it was doing. So start simple and iterate from there. And probably the other lesson we've learned, and again, there's always a way to do something. If you sit down and think about it long enough, there's always a way to get to an answer that the client, not so much the client wants, but an answer that is close enough to optimum. Key takeaways, I think I've covered some of these already, is genetic algorithms, great. There's other harnesses out there that would like to explore, such as reinforcement learning, that we continue to do so. Break the problem down. Don't try and eat the elephant in one go. And again, the parallel running there is a huge one for us. I will say that in some of these instances, it was necessary to give nature a helping hand. So rather than start off with a schedule that is, like a really primitive schedule, if I can put it that way, and then wait for it to iterate and iterate until it's a really more, a more optimum schedule, why not move it along a little bit and, start it with something that looks like a practical or pragmatic schedule and optimize from there? Or as our data scientist put it, we could start it so it looks something like Paul, and we could have it evolve into a data scientist, which was a rather cruel way of putting it, but that's one of the things we have done. So don't be afraid of doing that as well. Again, it's been a thoroughly interesting journey that we've been on. So that was it for me. Hopefully, I've got a few minutes for questions.
Thanks a lot, Paul. Any questions from the audience?
If I can see anyone.
Yeah. Hi, thanks for presenting this use case. It was interesting. And I'm interested in if you worked on some approach to reduce the load on the MIP computations. Like, have you considered anything like, okay, I don't need to solve MIPs for this chromosome because I know it will be infeasible or will not be good in anyway, this somehow, and you try to reduce.
Absolutely, that's what we went through that quite early on, and we continued to go through that when we set up the chromosomes as well. So when I say about giving nature a helping hand, let's maybe move it away from some of the infeasible things, but let's make sure we're not putting things in the MIP or the MIPs that you would never choose. I think that's something I learned early on in my career, that if you really, you can take the approach of just put everything in the MIP and be reliant on the MIP to pick the best things, but that obviously drives that drives the size of the MIP, the number of variables that you need. So we put quite a bit of thought not just into the chromosomes, but also into individual MIP. We did everything we could to keep the MIP complexity down, because obviously, not only does that mean that we get a solution more quickly, it means that it keeps the costs down, and we get an answer for the client, and more scenarios run more quickly. So absolutely, we did that.
Okay, thanks.
Okay. You have to hold it down.
Good question. Have you tested the outcome without MIP, just going all the way through with the algorithm?
Haven't tried that yet, no.
It would be good then to understand, okay,
Yeah, yeah. I think then if we were to try it without the MIP, we'd have to have some way of saying that, we could just do a simple backward schedule then. But I think if we were to do that, it would get quite complex to see, well, okay, because we know, I think we break capacity quite quickly. So then you're into, well, what do I pull forward? What do I push back as well? So something we can look at.
Which kind of crossover were you using? Was it 1-point crossover, and which kind of selection?
Oh, wow, that's probably a question for the data scientists. I know that the crossover point we picked, I think we started off with a random crossover point. I'd have to go back to the data science team and looked at that, but I know there were quite a few variables that determined at which point you picked the crossover and how many mutations you were doing. I think it was something to do, I think we looked at one over the length of the chromosome, I think was the number of mutations that we made. I'd have to go back to the data science team and check that, but I know there was quite a bit of effort went into playing with those variables as well. Happy to pick that up outside. Okay.
All right. Thanks a lot, Paul. Thank you.
Thank you.